Hi, everybody. So I'm an assistant professor. I just came to UC Berkeley last fall. So I only been here very recently, probably more recent than many of you here. So my research focus is on high energy astrophysics. So things that we survey the sky, things that suddenly brightens up and then fades away. Okay, so I study all these things called transients. So like the thing we're going to talk about today, there are also very rapid transients. So we study what's going on, after it fades away, right? The theorists have all, we collect all the data we can collect and then try to figure out physically what happened. Okay, that's, I'm a theorist. So I try to come up with theories to explain the observations and try to predict new things. So here, I'm gonna make some predictions over here. And also, for the students here who would be willing to work with me, welcome to come to UC Berkeley to talk with me, and then we can work together on things not only related to this. I also work on radio, some other transients in radio wavelength, in optical band, in gamma rays. I'm going to talk about gamma rays and in X-rays as well. Okay, feel free to interrupt me, and we can have a good discussion throughout the session. Okay, so here's an outline of my talk. Okay, so I'm going to talk about neutron star mergers. So we're going to talk about neutron star mergers. Okay, so how many of you guys already know neutron stars? You all knew, okay, you all know what neutron stars are. Okay, good, because I did not prepare an introduction slide for neutron stars. We all know. So we're going to talk about their galactic double neutron star systems. They're binary systems that are made of 2 neutron stars. And then we're going to talk about some observations on gamma ray bursts. Gamma ray bursts were discovered decades, like half a century ago. Only now we finally understood what they come from. And then I'm going to put some introduction on, there's a huge amount of work that has been done on neutron star mergers. We're going to touch in a tiny slice of it. Okay, still very, very interesting slice. Okay, I'm going to talk about some new work that we did, just put on our archive about late time accretion. That's going to be the main topic. Okay, so there are galactic, in our Milky Way, there are double neutron star systems. Many of you guys probably already know. So the way we discover them, they are pulsars, neutron star rotating pulsars. So you can look at their pulsation. So because if it is in a binary system, it has the Doppler effect. So when it's moving towards you, the pulses will be narrowly spaced between each other, and when it's moving away from you, so you see the pulses are farther apart, and that's the orbital period. So we have double neutron star systems with the orbital period somewhere between 0.1 days, basically a few hours, up to 100 days. So there's orbital modulation of the pulse arrival times, okay? And these pulsars have the spin periods are between 10 and 100 milliseconds. Very rapid rotating neutron star, okay? So in such tight binary systems, there are lots of GR effects that we can precisely measure, because we measure the arrival time to millisecond timescale, to millisecond accuracy. Actually, you can time them through many, many years. You can measure the upsidal precession. You can measure time dilation, basically electromagnetic waves propagating through a gravitational potential, and it has to lose energy climbing up the potential, okay? And it undergoes Shapiro delay, and it has, so gravitational, because the orbit, it has a time-dependent quadrupole moment. It emits gravitational waves, so the orbit will decay over time. So the orbit semi-visual axis actually shrinks with time, and that we can measure by time in the orbital period. We also have the precession. If you have a spinning top, which is the spin of the neutron star, the spinning top undergo geodesic motion, and that the spin direction will undergo parallel transport. And we can also have the GR effect can also be measurable. Okay, and a famous example is the Haus-Taylor binary. Okay, there are many galactic double neutron star, are roughly of order 10 known. So the upper maybe 2/3 of the table shown here are the ones that we know they're going to merge within the Hubble time, within the age of the universe. You can see the merger times over here. So you can the right column. So there's a TC is the merger time in giga years. You can see the first one is going to merge in 46 million years. So very quickly, that one is going to merge. Okay, very quickly in astronomical standards. Some of the ones you can see the merger time is extremely long for this one. It's extremely long. We're not going to wait until it merges. Right? So we studied this. There's a lot of information contained in the orbital period distribution, and then the merger time distribution and so on, and their masses, because we can time them very accurately. We can measure all these GR effects, we can measure the masses. You can look at some of these numbers. Let's say if you look at the fourth row, okay, J1906, and you go all the way to some of the masses, you can see how many significant digits. So we can measure these masses. Actually, some of these, the uncertainty is dominated by the unknown gravitational constant. Okay, so very, very accurate timing can solve all the lots of things. It leaves us theorists on wonder why the neutron stars, the neutron star masses are 1.3, some of them 1.4. Okay, a lot of theoretical things. So here is showing the two masses. So one of the mass, the horizontal axis, is the mass of the radio pulsar. Typically, it's only one neutron star is pulsating. The other one is not seen in the radio beam. There's only one case. It's the third row, J0737. It has A and B. So both neutron stars are pulsars. And that one, we can measure lots of other things. Because you have two pulsars spinning. You can imagine how many observables you have. Okay, most of the other ones, you only have one pulsar. Okay. But using those, you can measure lots of things. You can measure individual masses. So these are the constraints. So the constraints are extremely tight. Some of these are just one dot. It's not, but it's actually, if you zoom in, it's actually like a very narrow stripe of parameter space on the two mass plane. Some of the other ones we don't have GR effects measured yet. So you only have the total mass, but you can constrain them. But the inclination of the orbit is unknown. So you have these degeneracies and so on. So there are, let me mention this. So from the galactic neutron star systems, we know the rate at which they're going to merge is roughly about 30 per million years. So every million years, there are 30 of these happening, okay, in the Milky Way. And that's about, it's not close to 1%, but 0.3% of the core collapse supernova rate. So this is the rate at which neutron stars are made. And that is the rate at which two neutron stars merge with each other. So you can say that a few neutron stars out of 1,000 would have to find its companion and merge with each other within Hubble time. Okay. So one more introduction on gamma ray bursts. So these are discovered in the 60s, in 1960s, very, very long time ago, and people have studied them with all sorts of satellites. Today I'm going to introduce one satellite, which you guys may already know. This is a Swift satellite. It has two of the detectors we're going to talk about today. So you have the BAT, which is sensitive to gamma rays. So gamma rays come from all directions on the sky. It has a very wide field of view. You can see about a tenth of the entire sky. So roughly like this big of a size. All the gamma ray bursts within this patch of the sky, it can see, okay? Whereas the other two telescopes are really better telescope looking. So one of them is sensitive to X-rays. X-rays, you have to come the collimated telescope. So that one has a very, very small field of view. So once you detect the gamma rays, you can localize things to within about a few 10 square arc minute. And then you slew your X-ray telescope to that position. And then you can pinpoint the position because the X-rays, you have very, very precise sky localization. And there's also a UVLT, the UV and the optical telescope can also refine the position of these transients. So what happens shown over here is it's a very good example of this. So in a very early time, so here I'm showing in time axis in seconds. And in a very early time, within the first second, you see the gamma ray burst, right? It's one very brief amount of, it only lasts for about 0.03 seconds. It's very, very brief amount of gamma ray emission. And then after that, you quickly slew your telescope, slew your XRT, the X-ray telescope to that position, and you find that there's an X-ray source over there showing in black, and the flux rapidly drops. So what happens is the flux lasts for about 100 seconds, and then it rapidly drops. And then later on, you don't see anything for this particular source. And these are named in a very easy way. So this one was discovered in September the 5th, and actually September, May 15th. Okay, so this was I'll show you more. Okay, so you can see from this plot is that we have the prompt gamma ray emission we call prompt emission, and then there is X-ray emission which we call it's kind of flat. Although we don't catch the early half of the plateau, there are other cases where we catch the plateau in better way, which is a more long-lasting plateau. That's the X-ray plateau, and then it rapidly shuts off. Okay. And typically these plateaus last for about 100 seconds. And the fluence, if you integrate over time, the amount of energy that's emitted in the plateau is roughly comparable to the amount of energy that's emitted in gamma rays in the prompt emission. Okay? So there are many of these that are measured. Okay, these are the ones. So these X-ray plateaus are shown for this. These are the sources with known X-ray plateaus. They typically last for about 100 seconds. I'll later on explain some theoretical background why that has to be about 100 seconds, why they cluster about 100 seconds, why don't this plateau go all the way, to 10 to the 4 seconds and then decay. There are some underlying reasons behind this. Okay, so there are many of these. And after some of these, you have the bright afterglow. So we call it afterglow because it's very late. After hours, we detect this afterglow, fading afterglow emission. And what's understood so far in this gamma ray burst after half a century of research is the afterglow part. Okay, so only this afterglow part is reasonably well understood because the physics is rather simple. And the physics is well known if you look at one of the brightest object in the sky is Cygnus A radio galaxy. So this galaxy has a supermassive black hole. The galaxy is actually very, very tiny. You can't even see the galaxy. This is about 50 kiloparsecs apart. So it shoots out a jet. And it's also, we believe, also in GRB. GRBs also shoot out a jet. So the jet actually runs into surrounding medium and then gets stalled because of the shock interaction between the surrounding medium. And that's what's emitting synchrotron emission, and that produces this afterglow is seen in X-ray and also seen in optical and the radio band as well. Okay, that's I would say the only part that's reasonably well understood, including the decaying rate and then the spectrum and so on, the multi-wavelengths. But the early part is very much of mystery so far. So it's the early time emission that's before about 100 seconds that I'm going to focus on today. There is also a new things that one can do on the afterglow side, but we're not going to talk about today. Okay. So another thing, because by the time the XRT, the X-ray telescope is slewing, so the X-ray telescope looks like this. So by the time the X-ray telescope is slewing to your target, this gamma ray detector is still being used. Okay, still receiving data. Although for this particular event, GRB in 09, 05, 15, it was not sensitive enough to see much beyond the first 0.03 seconds. But for other events, the gamma ray detector still detects gamma rays. Okay, there are about a quarter of GRBs. The gamma ray detector still sees things. So this I'm showing time here in linear. The previous plots are in log, so it's in linear in time. This is in count rate. So the gamma is still counting gammas. Okay. So what's seen here is so there is an initial spike, which is the GRB, the prompt emission, which I was showing over here. So you can't see. So up over there. So that earlier one, that's a very, very, very bright spike. Okay. But after that lasts for about 1 second. And that 1 second is this a huge spike. It actually shoots all the way beyond the plot, beyond the y-axis of this plot. It's a huge spike, but there's some residual, detections over there. And this we call extended emission. And about a quarter of short GRBs show this extended emission recorded by the gamma ray detector. And again, the extended emission lasts for about 100 seconds, similar to the plateau that I showed earlier. And this, the energy, if you integrate over time, the energy is also comparable to what's emitted in the prompt spike. This gamma, it's a spectroscopically hard, and this is a spectroscopically soft. And most of the energy in the extended emission is actually emitted in the X-ray band. But sometimes our slew is just not fast enough to catch that. So our XRT only slews after about 2 minutes. And sometimes it misses, sometimes it doesn't. It does catch it. So these are the cases where it catches. So we come to the kind of roughly consensus that there is extended emission. So the engine, whatever is making these gamma rays, is active up to about 100 seconds, and then it shuts off. And then the jet propagates to large distances and run into other medium and produces the afterglow. Okay. So there are many models that has been proposed to explain this, long-lasting X-ray emission. Although it's short for observers, you have to react within a few minutes. Once there's a gamma ray burst, you have to really quickly decide if you want to follow it up and quickly slew your telescope within a minute. But actually, it's very long in our standard because we are talking about neutron star mergers. These mergers happen in millisecond time scale, right? 100 seconds is way longer than what a merger happened, right? So this is kind of a long-lasting emission in our theoretic standard. Long-last emission. There are many models trying to explain what they are. So there are maybe I would say a third of the theorists believe in this model, and a third of the theorists believe in this model, and probably a third of this theorists, including me, believe in this model, which I'm going to present today. Okay, so very, very diverse point of view on what's going on over here. So you can see how controversy and how much work one can do in theory. Okay, this fallback equation is that after the neutron star merger, the neutron star merged into a new compact object, which is what we call the remnant. There's some kind of marginally bound material, which is not going all the way to infinity, but it falls back on, let's say, 100-second time scale, right? It can have this long-lasting emission. And then the other one is the neutron star merger remnant is a marginally stable neutron star. It does not collapse to a black hole immediately. It stays as a neutron star lasting for about 100 seconds. And around this time, it suddenly collapses into a black hole. So the emission is shut down. Okay, there are these two camps of emission. The problem is that they have this one has to be extremely marginally stable. So imagine the neutron star merger happens on a millisecond time scale. So the remnant lasts for 10 to the 5 times that time scale. It did not collapse within 1 second, did not collapse within 10 seconds. It collapses all the way so late, about 100 seconds after that. So it's a kind of a fine-tuned situation. On the other case, on the fallback scenario, it's hard to explain why it rapidly shuts off, right? Because if you have things marginally bound, why beyond 100 seconds, there's no more things falling back, right? So these two problems will be solved in a third model. So let me do some introduction on the vast literature that have been done on neutron star mergers. There are a lot of things that have been done on neutron star mergers. So here's a schematic diagram showing 2 neutron stars at the final milliseconds. So this is showing in about 2.5 milliseconds. So the first one is minus 0.3 milliseconds before the merger, and then 0.6 millisecond and all the way to 2.5 milliseconds. So after basically a few milliseconds, the neutron star merged into a more massive, basically twice the mass of the individual neutron stars. And then there are some material that's unbound. So that's we call it a tidal tail. So that some material gets swing away, and that's a small amount of mass. Imagine a neutron material on the surface of a neutron star initially is very, very bound because neutron star is very compact. It's very difficult to launch some material all the way to infinity. You have to climb up this enormous gravitational potential, right? So only a small amount of material can do that. That's about typically 10 to minus 3 solar masses, but in general, throughout all simulations, it's less than about 1% of a solar mass. Very small amount of mass that's promptly ejected. And the uncertainty in here, there are many, many simulations done. The uncertainty here is the equation of state, like how big the neutron stars are, right? It depends on the equation of state of dense matter. Okay, so the next stage after the merger, so you have formed a remnant, which the fate of the remnant is still highly uncertain. So here is showing here is showing some 3 sets of simulations with different spatial resolutions. You can see that this smallest spatial resolution. So the neutron star individually is about 10 kilometers in size. So you can see these simulations are extremely high resolution, only 10 meter in resolution. So that's the state of the art. Nobody has done better simulation than those. So they all agree on this is of course for a particular choice of equation of state. There's also an equation of state uncertainty over here. So even if you fix the equation of state, what happens is that this you get, let's say you get this density profile. So you have a very, very centrally concentrated density profile, which falls off as a function of radii, okay? The problem is that you cannot resolve after the remnant formation is in a differentially rotational stage. This is showing the angular velocity as a function of radius. So at the very, very center is rotating very slowly, and then at the edge of the remnant, roughly at the edge of remnant, that's where the angular momentum is the largest. That's where the 2 neutron stars smash onto each other, and that's the highest angular momentum. And then beyond that is a Keplerian rotation disk, okay? So people have been struggling trying to resolve what kind of angular momentum exchange processes. You have differential rotation, there must be friction, right? The friction wants to bring the entire thing into a uniform rotation, meaning uniform angular velocity. And this has been really difficult. Even the small, you can see that it does not really converge very well. Within the first 30 milliseconds, you may need to run this thing for up to a second in order to resolve what kind of angular momentum transport mechanisms are there. So this is a unknown problem. We don't know when and how the remnant evolves. Whether and when does it collapse to a black hole, or does it actually ever collapse to a black hole at all? Okay, so that, and then the uncertainty is on the very, very small scale. You have to have very high spatial scales in order to resolve the angular momentum transport. Okay, and then the next stage. So my talk is going to be agnostic about what the nature of the remnant is. I'm going to assume that it's about a 3 solar mass, maybe a 2.5 solar mass black hole. Okay, it doesn't matter to it. I use Newtonian gravity anyway. So initially, this material that's surrounding the remnant, I'm going to call it a black hole from now on. It may not be a black hole, though. It's mostly made of neutrons because it comes from the neutron star interior, and there's a very small amount of protons and electrons. Okay. So during the first about 1 second, this is the viscous time. So the material would viscously spread because of differential rotation. You have this Keplerian rotation. So inner regions would rotate faster than outer regions. It would try to spread its, and it would try to transport angular momentum outwards. The outward material would spread outwards. That happens on a viscous time scale, which is about 0.1 to about 1 second. During that time, the system, the material that's outside of the black hole, is very, very hot and very, very dense, and the electrons are highly degenerate. And in that state, the system emits a lot of neutrinos, and these neutrinos are thermally emitted. They're about 10 to 30 MeV neutrinos, very high luminosity, as high as a core collapse supernova neutrino luminosity. Okay. And now the position has changed. The composition has changed. Now there's a protons, neutrons, and electron positrons, and photons. They're in thermodynamic equilibrium. Okay, and the temperature here is roughly about 10 gigakelvin at this point, about 1 MeV. Okay, if you use energy. So at the same time, we believe there is a jet because we see gamma rays, and the gamma rays come from a jet. We also see X-rays. So we believe there is a jet, but so far the simulations have not been able to produce a jet that is in agreement with the energetics that we infer from the gamma ray observations. Okay, so this is in a stage where we call it neutrino cooled disk. So it's undergoing very rapid. It's like photons are carrying energy away, so the disk can be cooled by neutrino emission. Okay, and the disk size is about several thousand kilometers. Okay, at this time. There are lots of simulations. I'm just pulling out a random one, which is the recent one. You can't see the citation here. It's in 2021. Okay, it's a very recent one. People have done simulations. You can see here is the time axis. Here is the mass. So mass is normalized to the initial mass of the disk. You do such torus simulations. That's, the mass gets depleted initially through accretion. So that's the upper panel showing the accretion rate, the rate at which the neutron star or black hole is gaining mass over time. Okay, so that's the accretion rate. And later on, the dashed line showing the ejection rate. So mass later on gets ejected from the system. And this mass ejecting is extremely important because if everything gets eaten by the black hole, we wouldn't see much, right? So there are mass that's ejected. Actually, we'll see that this mass contains nearly all the heavy elements, the heaviest elements on the periodic table, and we should be grateful of that. They made gold and platinum and so on that we were actually using. That's they all come from this mass outflow shown over here. Okay, so initially the mass gets eaten. So large fraction, you can see about a large fraction of the mass gets eaten by the black hole. That's during this neutrino cooled phase, and later on the disk is not dense enough. So neutrino emission, it depends very, very sensitively on the density of the gas. When it gets less dense, the neutrino emission basically shuts off. So later on, the disk is adiabatic. It stops cooling. Okay, so that's the second stage. We call it advection dominated. We can also call it radiative inefficient disk because radiation does not carry energy away. So now now the temperature has dropped because it's now volumetrically it's much larger than 10 to the 8, maybe a few times, maybe up to 10 to the 9 centimeters. It's larger than previously. So now the temperature has dropped such that protons and neutrons can combine into deuterium and then helium and all the way up to very high mass number elements. So I'm showing over here, all the elements are formed inside the disk. And at the same time, because the disk cannot cool, it's still undergoing this viscous evolution. So there's a friction which generates heat. And also there is a heat generated by fusion. You fuse from proton, neutron, and all the way to helium and all the way to up to heavier elements, and that releases nuclear energy. So this energy released by viscous heating and by nuclear energy, that drives the wind. So a large fraction of the mass of the disk. So initially the disk mass is about maybe 0.1 solar mass, and it gets depleted roughly around this time, roughly on a time scale of a few seconds. It gets depleted. So maybe only a small fraction of the mass will be left over, okay? And that's the work that has been done so far. So each of these stages, there are like tens of papers written. Even some of these stages are maybe hundreds of papers written over here. I can't give an overview over here, but what's unexplored is the evolution beyond about 10 seconds. Okay, nobody has done simulations past about 10 seconds. Okay, that's what I'm gonna focus on today. Okay, so the good thing is that beyond 10 seconds, the nuclei already formed. Okay, so the protons and neutrons, they already combine into nuclei. So it's actually quite complex. You have all the nuclear isotopes, a lot of nuclear isotopes inside the disk. You want to evolve this hydrodynamically, including the nuclear reaction happening inside the disk. So very, very complicated. That's why it hasn't been done yet. Okay. So, the question? Yeah.
So, go back to last slide.
Yes.
So basically, the model which is time independence and with the time difference, time they have.
Yes.
So now you get here and your access is the time. So whether you can use slope to get the effective temperature at some certain window to your eye.
Yeah, the problem is that these neutrinos we can't see. These neutrino, the number of our neutrino detectors are so inefficient. Oh, okay. So he was asking whether we can probe the temperature history, the temperature evolutionary history of the system. And the answer is very, very different, very, very difficult. We don't see the gamma rays. The system is completely optically thick to gamma rays. We don't see gamma. We only see the gamma rays from the jet, but the jet launching by itself is uncertain. We don't quite know. In terms of the disk interior, the only information we can get is from neutrinos. And the problem is that this neutrino luminosity, although the neutrino luminosity is extremely high, 10 to the 53 ergs per second, very, very high, but these events happen very far away in the universe. So we can't really detect these neutrinos. I think it's hopeless to detect neutrinos from this. If one of these happen in a Milky Way or in a very, very near, which you have to wait for, 10 to the 4 years or 10 to the 5 years to have one case happen. If it happens, we will see neutrinos, and that would probe the temperature in the disk. Otherwise, there's no information about the temperature in the disk. These are all theoretical, okay? The theory can make a lot of predictions, including, if we eventually get down to the full bottom of the story, right? We can predict kind of the gravitational wave emission, right? And we can predict the jet, and the jet will generate gamma rays and X-rays, and we can predict all the isotope ratios, and those will be indirectly used to infer whether our theory is correct, okay? Question? Yeah, these jets are relativistic jets. So the material here is moving at Lorentz factor about 100 or higher. So it's through some magnetic processes, which theorists we have not converged on. But I have my personal opinion on, which I think it's due to the spin of the black hole. It launches the electromagnetic dominated outflow, which can get to very, very high Lorentz factors, like hundreds, even to thousands. And that carries a lot of energy, and a fraction of that energy is emitted in the gamma ray band and X-ray band. Okay, and that's the jet. Feel free to ask any questions along the way if I do not do the introduction in a proper way. That's a great question. Thanks. Because other people may also have the same questions. Okay, should I move on? Okay, so thinking about nuclear reaction, let's look at what the sun has. Okay, the sun is a very typical star in the Milky Way, so it's abundance. So I'm showing the abundances versus mass number. So one should be hydrogen, it should be 1, and then helium. And I'm also showing the astrophysical origin. So these are also theoretically expected astrophysical origin. So the Big Bang made the first two, hydrogen and helium, a little bit lithium. And then stellar burning, so nuclear reaction inside the core of the stars. And then supernova explosions. They made the elements all the way up to iron, but they're not able to make this new supernova explosion are not able to make this. So these heaviest elements, they are highly neutron rich. I'll define neutron rich very soon. So there are only a millionth of a solar mass, okay, in the sun, a millionth of the mass in these heavy elements, and they're so important to our everyday life. So we want to understand what their origin. So you can see that the abundance pattern has a couple of peaks, okay. So there is this, we call this is the first peak, although it does not look like a peak, but it's actually there's a little peak over here because there's drop here. There's a second peak, and then there's a third peak. There may be another lead peak over here, but it's not very resolved. There's also a little bit of a bump. So it is first peak, second peak, and third peak. So the physical reason of these peaks are very, very simple. So they are due to this closed shell structure in nuclei. So these nuclei are especially stable, okay, because of the closed shell configuration. If you have 50 neutrons in a given nucleus, it will be exceptionally stable. So 82 neutrons and 126 neutrons, okay. And you can see each peak has two sub-peaks, and that is also due to nuclear physics. It's the detail about, I think these broad things are well understood. It's the detailed kind of abundance patterns that is still mysterious. There's a lot of uncertainty on nuclear physics that we're still working on, okay? And I'll show you some of this. Okay, so this question?
Yes, so in this slide, like more the
yes,
mostly like pairs in R process and S process, but in the end you only show one. So is there like also R process or
yes, there should be one, but it's also there's also some germanium production from supernova. So you can see that this one is basically supernova peak, and that actually polluted this peak. If you can somehow subtract the supernova part, and you will see actually it does have two peaks. And theoretically, we also expect two peaks. Okay. Yes, we don't see that very clearly, but it's there. Yeah. Okay. So the physical reason, as he was mentioning, is that there are two different processes. And so this is showing a neutron number and then proton number or atomic number over here. So these are the stable nuclei over here. So these are the known stable nuclei with decay time, infinite decay time. And in order to produce many of the heaviest nuclei with mass number more than 80, that I'm focusing on, you have to have neutron capture, okay? Because supernovae, they are not they are incapable of making this. So there are two ways you can do these neutron captures. One way you can do it through S process, so very, very slow neutron capture. So basically you capture one neutron and then it beta decay. So beta decays go diagonally, this diagonally, that way. You can see the little vector over here. And it captures one neutron horizontal, so it moves horizontally, and then it quickly decays, and then it horizontally goes like zigzag, and all the way build all the way to the heaviest elements. That's slow neutron capture, and that happens in late evolutionary stages in low mass stars between maybe 1 and then a few solar masses. Okay, and there's also rapid neutron capture, which happens in neutron star mergers, where there's a huge amount of neutron flux on each nuclei. So what happens in this rapid neutron capture is that a given nucleus, let's say if you sit here, it captures a huge number of neutrons, let's say 10, let's say here 20 neutrons, and until it gets so far away from the stable valley, and then the beta decay time is really, really short, maybe like a millisecond or even shorter, even up down to like a microsecond, and then it stalls over there. Okay. And it keeps going, it keeps building up. Beta decays only a little bit, and then it keeps capturing neutron, and it goes zigzag over here. So here there's a magic neutron number 82, which signals a very stable nuclei over here. So their neutron capture cross section is reduced for those ones. So they stay here. They also do a little bit zigzag over here, but only in a neutron number of 1. Do a little bit zigzag over here, and they keep going. So that's the R process path. And from the R process path, you see that elements are made over here. And then by the time the neutron capture ends, they were going to decay back to here, right? Let's say if the mass for the same neutron number, let's say 126, these ones would have a smaller mass number than the S process would made. So you can see that it forms two peaks. Okay, so the R process makes a peak at a lower mass number. So that's this, let's say this peak. And that the other peak is the slow process, the S process. Okay, more graphically, I'm going to show it in this way. So basically, this nuclear reaction, you're looking down this valley. So the elements that are most stable, so the stable elements are here in down the valley. So upper here, they're more stable. They're more unstable over here. So basically, the system wants to evolve down the stable valley is here. If you zoom into the into, let's say, one part over here, if you stand over here, what happens is that the system captures neutrons. So these are iron 59, 60, and 61. It captures lots of neutrons until you're basically climbing up the hill. And then until it becomes so unstable, it beta decays, and it beta decays to this one. And then you can further capture neutrons. And you do zigzag and zigzag, it can do all the way to a very high mass number elements over there. And these are happening. So I have a movie showing over here. So again, this movie shows this is a neutron number, and then this is the proton number. Initially, the system is in very high temperature. Here you can see the temperature is 10. I can't really point it in the upper half. You can see the temperature is about 10 gigakelvin over there. And I'm going to show a time evolution of the abundances in this nuclear chart. Okay, so I'm showing over time. You can see over time, because there's a huge high neutron flux. So the system gets very, very neutron rich. It deviates far away from the stable valley, and then later on, when all the neutrons are completely used up, and then it undergoes beta decay. Okay, so you can see it makes these peaks. That's the first peak, and then the second peak, and then third peak. There may be another peak over here. That's the actinides. So it makes basically it goes from let's say if you focus on the third peak over here with neutron number of 82, that's where most of the mass from our process will be, and then it decays to here. Whereas if you go the stable S process, you will end up in over there. So that's why there are two peaks showing an abundance plot. Okay, the previous one is showing. You can't really see here the projection. It's showing in the nuclear reaction actually inside. So I'm gonna go back to my schematic plot. So the nuclear reaction is happening actually in the wind. So the material that's leaving the system in the wind has a very rapid expansion time. That's the expansion time, very, very short expansion time, like millisecond expansion time. So so that's the one I'm already showed. I'm also gonna show the other case with the 0.6 second. Somehow I can't get rid of this. Somehow I can't. It's a 0.6 second time expansion time, and in this time I'm showing the nuclear reaction inside the disk. Okay, so in this particular case, you still have very high, very neutron rich. Oh, sorry, because I moved. You also have very neutron rich saturation, and then you still undergo. So initially, it's because this expansion time is very, very long, so it does not undergo our processes yet. So now it starts because initially it was too hot, so all the high mass number elements would have been photo dissociated. So now it's allowed, and then it does not go all the way to very high mass numbers, but it goes all the way only to the second peak. So inside the disk, the R process is very different from in the wind. Okay, you can see that in the entire system, there's a lot of uncertainty here in whether what final abundance you get, right? Whether you have R processes inside the disk or in the wind. Okay, so I'm gonna flip back and forth and just to show you the two different cases. So this is a case where the temperature stay high. The temperature is showing in the red line in the left upper corner. The red line, the temperature stays very high for that particular case. And this one is a rapid expansion case where the temperature drops very quickly. Okay, so they show very different abundance patterns, right? This one goes all the way to very high, very heavy elements, and whereas the other one goes only up to the second peak. What was the question? Yeah, here, those are fission. So these very, very high mass elements over here, they're all the way up in the upper right corner, the gray zone over there. They're undergoing the fission, and they actually split in half, roughly half. So this maybe 200, they actually split in here between one nucleus over here split in half. Or one of them it would be 100, the other one maybe 120 or something. So they good question. Okay, so actually this is our process. I think this is a new frontier just to understand what elements were made in these neutron star mergers. But there is a lot of theoretical uncertainty because we don't know about the mass of these elements. They cannot be measured because their beta decay time scale is very, very short, milliseconds or even shorter. It's very, very difficult to experimentally know the masses of these isotopes and then their half-life time. So we need more lab effort in this direction. This is the data back in 2016. Now probably people have made some progress already, but this is far from enough. So all these isotopes are really unknown. So their masses are unknown. Their lifetime is also unknown. So we're all making use of theoretical guesses in these calculations. The entire R process path is kind of uncertain in the uncertain region. Okay, so I'm going to get to the late time accretions. Okay, the late time accretion, how we're going to model the late time accretion. So kind of a semi-analytically, this is just to get this sketch. We are planning to do more detailed numerical studies. So we want to model how much, this is a disk mass. So how does the disk mass evolve over time? So there's a disk mass. There's the size of the distance from where most of the mass is to the central black hole. We're going to model M and the time evolution of the disk mass and the time evolution of the radius of the disk radius. So we're using a simplest one-zone model. So the mass evolves over the viscous time. So after one viscous time, the disk mass would evolve. This m dot is given by the total mass divided by the viscous time. And also due to angular momentum conservation, the disk viscously spread outwards as it grows in radius. So the radius increases. Actually, it should be positive sign here. Sorry about that. And then the viscous time is given by some viscous. We don't understand the details about what's providing the viscous. So there's we use this alpha prescription. So the alpha prescribes the viscosity here. So that gives us the viscous time, which depends on the disk height, how thick the disk is, and then depends on the Keplerian rotational frequency, angular frequency. So one can easily solve this and then get this self-similar solution, which I will later on show you more of a numerical solution. So the disk mass gets drained very slowly on like time scale of seconds or even longer time scale. So it goes as time to the minus 1/3. And the disk radius increases as t to the 2/3, basically Kepler's law, really. So what happens is the binding energy of the disk. So binding energy per unit mass in the disk, which goes as 1/r, it goes down as t to the minus 2/3. So the disk becomes larger and larger. It becomes less and less bound because its binding energy is dropping with time. Okay. And at the same time, you have to remember the material here, they're made of radioactive elements. Okay, these are radioactive elements that are going to decay over time. They have beta decays. So this beta decay, we have done this calculation showing that the heating rate due to beta decay. So we'll focus on the time scale longer than about 10 seconds. So there's many different calculations that we show that the heating rate due to radioactive decay is roughly given by this power law. Okay. So it's a power law that gives you, if you put in this power law, you can calculate how much cumulative heating there is. Basically, multiply the heating rate by the time, and that gives you the cumulative heating, right, over time. And that one, because this one goes as t to the minus 4/3, and multiply by time, you get t to the minus 1/3. What you get is that this cumulative heating goes down as t to the minus 1/3, whereas I was telling you that the binding energy goes at t to the minus 2/3. So the binding energy actually drops faster than the heating rate, okay? At some point, these two power laws are gonna meet each other, okay? And that's gonna be happening at sufficiently late time. And when that happens, the disk will become unbound because the heating overwhelms the binding energy, okay? We did different calculations of different expansion time shown over here. You get this universal heating rate, actually. So it does not depend on any of the other things. So once you put this energy heating in the energy equation, you add one more equation, you can solve for the disk temperature, and you can find that at some point, the disk will be unbound. And the unboundness is captured by this Bernoulli parameter, basically showing that how bound the disk is. So we prescribe when the disk becomes unbound, meaning Bernoulli parameter, meaning the total energy is positive, then it should get blown away. So that's our new calculation showing over here. I'm going to show you a numerical solution. So the solid and dashed line shows different prescription in wind. Okay, so what happens is that the disk mass initially evolves as t to the minus 1/3. And then at some point, which basically roughly about 100 seconds up to 1,000 seconds, depending on this alpha parameter, and then it suddenly becomes unbound. So material gets drained away. So it blows away a lot of mass from the disk. And then we think the disk must evaporate because of radioactive heating. And then that happens about 100 seconds. So we believe this is the reason why the X-ray light curve, it lasts for about 100 seconds and it rapidly drops because the disk is no longer there. There's no more accretion, okay? So from this, we also estimated that at sufficiently late time, because of the evaporation, this mass loss at, let's say, 100 seconds, the mass loss is going to contribute to the kilonova emission, okay? And it contributes. So here I'm showing the velocity distribution of the outflow. So typically what previous work have focused on the red line, the faster ejecta, whereas here, because the material is less bound, it is ejected at a slow speed. So we predict that there is some about 0.01 C outflow from the disk, okay? And that will contribute to the volumetric luminosity of the kilonova, which will be detectable by GWST at sufficient late time. It contributes about 10%. But in order to determine what elements were made in these outflows, you need this slow outflow because slow outflow will going to give you very narrow lines, either narrow absorption line at early time and narrow emission line at later time. You can do spectroscopy and then find which elements were made in this system. So these are the predictions of our. So this is my summary slide. So to summarize, so initially the disk mass is about 0.1. And this is the time when our process starts, okay? And then our process starts, and then you have a lot of mass loss from that process. And then later on, this is the new model here. We model the disk. You have this long-term accretion, and then towards the end, it evaporates because of radioactive heating. And then after that, there will be no more disk. And then we also model the jets and so on. You can ask questions about the jet and different viewing angles and so on. We see different phenomena, but I don't have time to go through that. But this is the final slide. Sorry for going over time. Okay, thanks.
Yeah, hello. So when you say that the whole disk evaporates,
Yes.
Does it include the dark matter or it's just the normal nuclear matter?
You mean dark matter?
Yeah.
So we don't model dark matter. So here the density of the normal matter is so high, so much higher than the energy than the density of dark matter, which is so we don't consider dark matter at all. So dark matter density, in the solar neighborhood or everywhere else, basically most of the space in the dark matter energy density is very, very low. It's rough. It's even less than one particle per cubic centimeter, right? So small compared to here. These things are extremely dense, maybe 10 orders of magnitude, or maybe 20 orders of magnitude denser than dark matter. So that's negligible.
Okay. And one more thing, when you like in the introduction slides, you showed the density as a function of distance. So is it the same for the particle species, or is there any interesting distribution for other particles? Yeah. So the rho plot.
Yeah, these are just baryons. So these are just protons and neutrons at this time. These are only 15 milliseconds. So this is completely dominated by free neutrons and free protons at this time. Yeah.
Okay, but if we see other, so other particle species are not abundant at all.
Yeah, because the other particles would have been photodissociated. They would have been because now these things are very, very simple. Only the fundamental particles exist. Anything that's more complicated, let's say deuterium, would have been broken apart easily.
Okay, thank you.
Yeah. Those heavier elements would only exist when later on, temperature drops, and then they will exist. That's at later stage.
So I want to ask why some neutron binary system have one pulsar while others have two. How does a pulsar come from?
Yes. So his question was why some of them has one pulsar, why some of the other ones have two pulsars. Is that the question?
Yes.
Yes. So these pulsars, they're let me show you a schematic diagram. Let's just look at this diagram. These pulsars, they only pulse within, it's like a lighthouse. They only emit radio emission along a very narrow beam of angle, okay? Only when you're fortunate enough your line of sight is fortunate enough to be within that opening angle shown over here, you can see radio emission. Maybe the other one also has some radio emission, but it's narrowly beamed. It's mostly likely beamed away from us. So it could have some very low level of radio emission, And most likely it's because it's beamed away from us. So we only see one pulsar. There is one case where you can see the third row, A and B, and the pulsar B actually sometimes its radial beam is beamed towards us. We can see its radial position. Sometimes we don't. So because of GR precession. So okay. So there are it could be the other cases they are like permanently beamed away from us. Okay. Whereas for that particular fortunate case with A and B, occasionally we see the other pulsar also in our B. The beams are very narrow. Those are probably like 1% of the sky. A very, very small beam. Okay.
And I also want to ask some off-topic questions, if you don't mind. So can you infer the mass and radius of each neutron stars from like the X-ray, gamma ray observations?
Very hard, extremely hard, because they are already destroyed by the time you see gamma rays. So
you
right.
even cannot do that with some theoretical models.
It has some individual. We can how to say indirectly infer the radii. If the neutron star, if the equation of state is such that neutron stars are big, then they are easier to it's easier to tidally disrupt them because they are less dense. So then you would have more ejecta, more tidal tail ejecta. So that's indirectly inferred, but it's not from the gamma rays that the jets and so on, because you have to go through so many levels of uncertainties, right? After you have gone through so many levels of uncertainty, you don't really know whether your inference is actually accurate or not. You basically have lost the information.
But you can do it with the gravitational wave.
From gravitational waves, yeah.
Okay, thank you.
Still difficult.
Hey, Fernando. So this is just like since we're on this plot, what's good with this, I guess, naming convention that y'all use for the pulsar names? Like, why do some have plus signs? Why do I have some minus signs?
Oh, these are just coordinates. So it's the sky coordinates, the RA and DEC. So on the sky, I don't remember exactly what like whether it's degree and arc second and so on. These are just coordinates on this sky position. So there's nothing really any physical there. Yeah.
And then I guess like a not so trivial question, but with respect to, I guess you were talking about earlier, the density of the actual object that you're looking at is matter dominant and is highly dense. And I guess like for me, I kind of sort of want to be able to map this out in the phase diagram of QCD, right?
Mm-hmm.
So I did see that there is a mention of a temperature that you have in the range between 1 MeV to 100 MeV in the whole evolution. So with respect to like a baryon density, like a mu B, where would this be placed in the phase diagram?
Yes. So these disk material I'm talking about are much less dense than the things you're talking about. You can see the mass density row here in gram per centimeter cubed. So we're talking about like hundreds of kilometers away from the central engine. So probably all those like equation of state and QCD stuffs are all the way near the center over there. And that's where these things would matter. Whereas here, we're talking about the disk at much farther away, much farther away. So they're much less dense, just normal matter. So the pressure is just the normal Boltzmann, the maximal Boltzmann distribution and matter.
One question, how do you determine your initial case?
Initial case?
Yes, so about the cooling disk, how do you determine? Like, I think it matters a lot about your initial mass and the initial radius of your disk. So how do you determine that?
Yeah, exactly. That's a very good question. So it's you have to start from the emerger, okay? You have to assume some equation of state on how big the neutron stars are, and then you have to do the dynamical GR, the dynamical space-time GR simulation, and you start from there, and you can model how much. Let's say here you have to start from there, but they only run to like a few milliseconds. You have to make some. There's some gap between here and then all the way to our disk simulation, which are on time scale of seconds. You have to start from somewhere. So basically you idealize this into some axis symmetric distribution of mass. Maybe you take that mass distribution and you say it's axis symmetric. You take this Keplerian part and then you model the outer part of it. That's where my initial condition starts. Okay. Yeah.
So you talk about the equation of state, you think it's an uncertainty. So how is that possible in the Earth lab to, I know it's impossible on the Earth to simulate, to reflect the neutron submerge, but how is it possible on the Earth lab to reflect a similar equation of state?
Oh, to simulate these extremely high densities, I think it's impossible at this point. We have to just rely on astrophysical measurements. in terms of lab, we can simulate probably like a white dwarf density scale, but these densities are just enormous. I don't think you may be able to do like high energy, like particle reaction, but I think these density scales is very difficult. Astrophysically, in some cases, we can measure the size of a neutron star and use that to indirectly infer the equation of state, but it's a constraint. It's not like a measurement. Whereas I would say the nuclear masses would be more appropriate. If let's see, where is it? So the unknown nuclear masses over here would be directly measurable by beam experiments, and that would be simpler to do than the equation of state.
What further from the low energy or the medium energy? The S.
Yeah, S process and R process. You mean it is proven to be happening?
Yes.
Yeah. Yes, it is. So the S process is in good agreement with the stellar abundances that's measured, and then the R process, we're just being able to do this, right? We're just seeing this. But the problem is that for these neutron star mergers, we have not. Let's say if you predict something like this abundance pattern, we have not been able to actually go to a neutron star merger and then actually measure what elements were made in that particular example. We don't know. We need the spectroscopy data, right? We don't have that yet, but we will probably at some point we will know some of these elements. Other questions?
Hi, I'm Tommy Sang from Kent State University. So I have a follow-up question on the other question. So one of the previous question was about dark matter, and you mentioned that the density of dark matter is so low that it's negligible.
Yes.
But dark matter is not uniformly distributed, right? Given how dense neutron star is, they can concentrate in neutron star to have a visible effect, right? At least I know that if we try to infer neutron star equation of state from nucleus equation of state, the contribution of dark matter is a source of error that is not negligible.
Yeah, that I don't know about dark matter. My understanding of dark matter is that it's only gravitationally interacting, but it could have some other interactions that are unknown, that not known in our lab. If it is only like a gravitationally interacting, like now a matter that's low mean density. I mean, low mean density from galaxy rotation curves. We know that the total mass in dark matter, if you distribute them in kind of a smooth way in the galaxy, then the mean density is very, very low. And then the neutron star, if it only works gravitationally, it's very difficult for a neutron star to gravitationally concentrate a lot of dark matter. Okay, that's through bounty capture. It does not capture that much dark matter by itself. So the amount of dark matter that would have accumulated over neutron star's lifetime would be very, very low. That's my expectation.
Do you know how low?
It would be absolutely tiny, but I don't remember how low it is. Typically, these are unbound particles. They don't really dissipate. So even if it comes in, it will just fly away. It will come in and fly away. If it does not have any interaction other than gravitational.
Okay,
because it's unbound.
Thank you. So this is Tom speaking. So I have a question that's like kind of unrelated, but is in the broad sense related. So I remember like a few years ago when LIGO announced that they have observed like some gravitational wave observations on like neutron star mergers. Are we talking about like the same type of objects right here? I mean, those that you just showed on the table, we wouldn't probably be able to see it because they won't actually merge like within anywhere quite soon, right? No. But are they like going to be some similar type of objects?
Yeah, these will evolve into the LIGO detected neutron star mergers. So LIGO only saw the final seconds before they actually collide onto each other. But these ones are still millions of years, actually hundreds of millions of years before they merge. So these are the progenitors of the LIGO sources.
Right. So basically, when you talk about like later on, when you talk about like the spectrum that you see, so these are like somehow kind of like the EM counterpart of the LIGO observations after like we actually see it, right? So
these are before.
No, like the ones that you just talk about. Like
those are the afterwards. Exactly. So after the merger, you have all the baryonic effects, right? All the accretion disk and jets and so on. And you see the emission exactly.
Okay, but so I guess like I know I'm just like digging down a rabbit hole here, but like my question I think really is like, if you only see, so what is the scope of like these? These are like those within, I don't know, the Milky Way or?
Yes.
Okay, but those that we do see, like actual merging like processes like way farther than this, right?
Yes, exactly. The ones LIGO sees
Mhm.
are way farther than the Milky Way. They are like 100 megaparsecs away, so much, much farther out than the Milky Way.
All right, thank you.
Yeah. But Milky Way is nothing special, right? It's just a normal
Right.
galaxy.
Like the physics is gonna be the
So
same.
all
yeah.
galaxies should have these neutron star, double neutron star systems in them. Right.
Right. Yeah. Because I was mostly asking because like I was assuming that they are like mostly of a few solar masses versus like I know there's sometimes like there are supermassive black holes inside and they're like completely different stuff.
They're completely different. Yeah.
Okay.
Yeah.
So my question is, maybe you already mentioned it in your talk, but so for your theoretical work, will you at some point need some input from experimental observation? Like, what is the observables that that are important for your work?
Yeah, there are two things I would really hope to get experiments input. One of them is this missing data in nuclear masses. Okay, the nuclear masses determines if you capture a neutron, how much mass you're going to lose, right? How much energy is released. That we don't know. That I hope to get. The other one is the atomic physics, which is not related to nuclei. The atomic physics of these high mass number elements. Let's see these ones. These high mass number elements. So we don't know what spectroscopic lines they're going to produce, right? We will definitely get a JWST spectrum out of these neutron star mergers soon, but we don't know which are the elements that are dominant in the line emission at late time. Okay, let's say a month after the merger, we'll take a spectrum. Which lines do they come from? So this atomic physics, because they have hundreds of electrons, you can imagine how complicated is it to model their atomic physics and the transitions between them. There's so many lines per atom. So that is another aspect I would hope to get lab help, I would say. You can only statistically measure them, really. You can't really use the lab data in like line by line. Yeah.
Like, so those lab measurements will help your work, but say that I don't know, like say at will you? I don't know, for those astronomy experiments, like do you like do you
observations?
Observations.
I see.
Sorry.
Not lab yeah, exactly. Observations, exactly. So we're gonna have a late time JWST observations. So at sufficiently late time, so I showed that this JWST can actually detect anything above here. So even 100 days after a neutron star merger, JWST should be able to measure this late time emission. And because we predict very slow ejecta, 1% of the speed of light, it should have very narrow lines, only 1% of the wavelength, delta lambda over lambda of 1%. There should be very narrow lines that will show up in JWST spectra at late time. So we should see this. So that's one of the things we can see. We can use. There are also some other like jet-related afterglow predictions, which I don't have time to go into. But yeah, more observations are definitely welcome.
Hi, I'm Diptanil, and thanks for a nice talk. I was wondering if, on the basis of like relative abundance of elements in the star, can you differentiate between, say, neutron stars from old galaxies, like really old galaxies versus like the newer galaxies?
Oh, you mean do neutron stars differ?
Yeah, like in their relative
over
abundance.
time,
Yeah.
or from galaxy to galaxy. I don't think because neutron stars are basically made of they're determined by fundamental physics, right? The neutron stars should not differ so much. If it is as a two neutron stars in two different galaxies, one elliptical galaxy, one spiral galaxy, if they have the same mass, I would believe that the two neutron stars should be identical. In what we care about, there may be, magnetic fields may be slightly different, their evolutionary history may be different, age may be different, but I would say they should be very, very close to each other.
Let's thank Wenbin again, and
thank you.